In this session we will be looking into nonlinear regression. So, nonlinear regression can be done by two methods. One is using nonlinear least squares optimization, right. The other one is, for some models we can employ data linearization technique to convert the nonlinear model into a linear model. We will be looking into both of them. So, cases wherein it is possible to convert a nonlinear model into a linear regression problem using data linearization, we will do that. Right. For cases wherein it is not possible to convert into linear regression, we will employ nonlinear least square regression. So, now let us look into the nonlinear regression. Right. So, let us say we are given this x and y data. Let us say we have been given this x and y data, and we are required to fit this model y is equal to c e power a x. So, y is given, x is given, right. So, now we need to fit this model. Basically we need to find out what is the c value and a value, such that this model would best represent the data that we have. So, we apply the same concept again, right. So, sum of square of residual. So, your observed data point is yi, the model is c e power a xi, where xi is the value of the ith value of the independent variable. So, this is the error associated with the ith point, square it and then sum it up. So, that is our objective function, right. So, now our job is to find out the value of c and a, such that if you do dou SR by dou a and equate it to 0, similarly determine dou SR by dou c and equate it to 0. Again over here you need to carefully differentiate it. So, 2 times this expression, and then you are differentiating with respect to a. So, xi would be a constant. So, xi e power a xi. So, remember the differentiation of e power mx is m e power mx, right. Again here remember m is the constant. So, in this case xi is known, right. So, what is unknown here was x, we were differentiating with respect to x, here we are differentiating with respect to a. So, that is why you have this c into xi, not a, right. So, this if you calculate dou SR by dou a and dou SR by dou c, you will end up with two equations equated to 0, we will end up with two equations, and in this case these two equations are not linear, those are non-linear equations, right, in terms of a and c. So, you can apply any technique that you know, for example Newton-Raphson method, to solve those equations, right. Two equations into two unknowns, if you solve them you will get the value of a and c. That is how we can fit the model, right. So, for example, if this is our data set, right, and if you solve these two equations, right, we will end up with c is equal to 1.61 and a is equal to 0.38, right. We will not be showing you how to exactly solve this nonlinear equation because we assume that you would have done that in your first year of engineering, right. So, we will quickly show you how to do that in MATLAB, right. So, for those of you who are new to MATLAB, we will have a separate video wherein you will be able to understand the same thing, how to solve nonlinear equations. Over here we will quickly brush through. So, this CLC, as you know, will help you to clear the command window. Clear will remove all the variables, clear the variables from the MATLAB workspace, right. So, here we are defining a function handle. So, the name of the function handle is fun, FUN, right. It is a function handle, right. So, prob is the function. So, we have the problem is going to be stated in a separate function file known as prob, right, and that name of that function is being assigned to this variable fun. So, that is why we have the symbol @ symbol over here. So, fun is now a function handle. So, whenever we access fun, we will be actually accessing this function prob, right. So, for solving nonlinear equations in MATLAB, you can use this fsolve command, right. For fsolve we need to give the equations that we want to solve and the initial starting point. So, here we have two variables. So, here we are going to arrange in this format that the first variable is going to be a and the second variable is going to be c. You could choose the other way, but we have chosen this way and we will be consistent it throughout, we will be consistent it with throughout, right. So, we are giving a guess value of a starting value of a to be 1, and a starting value of 0.5 to C. So, these are the two. In the function file we are going to return the value of the two equations, right. So, for solving, for using fsolve, the equation should be in this form: f of x is equal to 0. So, if we have two equations, both the equations right hand side has to be 0. So, whatever we have on the left hand side is to be given to the equation, right. So, remember this is our equation, these are the two equations that we have, right. So, z is what we will get from fsolve when it is solving, right. So, the first value of z would be a, because that is the notation which we have taken and that is the order in which we have given the starting point, right. So, the first value of z is going to be a, the second value of z is going to be c, right. So, once inside the function we have decoded it, and then these two expressions are nothing but the left hand side of these two equations, right. So, here if we see x is a vector, y is a vector. So, we use this dot operator x dot star y, and this e power a x I is going to be n times for n values of x. So, again a dot operator dot star exponential of a star x minus c is a constant, right, and because of this summation we have this sum. So, sum function will help us to sum all the values, right. So, this x I is this x vector x, right, this vector x, and then we have this e power 2 a x I. So, exponential of 2 into a into x, and since this is going to be a vector, again we use this dot operator. Similarly, we have written this second function, right. So, this is the first function, this is the second function. Now, if we run this code, right, it will repeatedly it will access this function file multiple times, right, and at the end of it, it will give us these two values, x is equal to 0.38 and 161, right. So, since we had used this convention that the first value is a, the second value is c, a is equal to 0.38 and c is equal to 1.61, right. So, those of you who do not know MATLAB, maybe this part you may not be comfortable with this part, but that is fine. The rest of the discussion is not going to be dependent on this one. So, it is totally fine if you have not got this MATLAB section, right. Another way to solve this nonlinear regression problem. So, sometimes this is possible to do, right. So, our model was y is equal to c into e power a x, right. So, what we can do is we can take ln on both sides. So, ln y plus equal to ln c plus ax ln e, right. So, ln e is 1. So, we will have only ax. So, now if we see this model, right. So, y is known, right. So, in this case remember x and y were given. So, y is known. So, we can calculate ln of y, right. So, let us call that as capital, let us denote it with the uppercase y. So, if this lowercase y is given, we can calculate the uppercase y using this transformation. Let uppercase x be the lowercase x, right. So, what we are doing is we are equating it to y is equal to this is a naught plus a1 x, right. So, we are basically plotting, we are converting it into a linear regression problem, right. So, the uppercase x is nothing but the values which we get directly, only the y has to be transformed, and when we solve, what we will get is a naught and a1. The a1 would directly correspond to this a in our model, whereas the a naught which we get is not does not represent c, but we need to take the exponential of a naught to actually get the value of c, right. So, here what we are doing is the nonlinear model which we have, we are doing data linearization to convert into a linear form, and then we can apply the same general linear least squares which we discussed, right. So, in this case for y is equal to a1 x plus a naught, the z value is nothing but 111, right, because we have a constant coefficient, and the second vector is nothing but the x values, right, and z transpose is the transpose of this, right. So, we can either use this to solve or we can use this to solve, right. So, in this case remember this is capital Y, summation of uppercase y, and uppercase y is to obtain from this transformation. Similarly, after solving we will get a naught and a1. To get c we need to again use this expression. So, let us consider that we have been given data, let us consider we have been given this data, right. So, there are 5 data points where x is the independent variable, y is the dependent variable. As of now ln of y is not given, right. So, ln y is not given, we will come to that why we are finding ln y, right. So, the model that is given is y is equal to c exponential a power x, right. So, either we can solve it using nonlinear regression, or what we can do is we can take ln on both sides, right. So, ln y is equal to ax plus ln c. So, ln y can be represented by capital Y, right. So, we will use uppercase Y as ln y, x let us say is the same variable x. So, we are basically comparing it to y is equal to a naught plus a1 x, right. So, here if we see this is a constant term, right, this is the independent variable, it has a constant, right, this is the dependent variable term, right. So, we can calculate y, we can calculate x. So, a1 is nothing but capital A and a naught is ln c. So, we are comparing this model with this model. So, if we use this variable transformation, this model will boil down to this one, right. So, using general linear least square regression, we know that the solution for this problem is z transpose z into A is equal to z transpose y, where z is a column of ones, right, because we have a constant coefficient term and the x1 variable stacked, all the endpoints stacked like this as second column, right. So, and then once we know z, we can calculate z transpose, similarly we can calculate z transpose y, right. So, if we apply this solution to this problem, right. So, our z matrix will be a column of ones, there are 5 data points, so 5 rows, and then this independent variable is to be directly stacked over here, because we do not need any transformation of that, right. Uppercase x is nothing but the lowercase x. Once we have z, we can calculate what is z transpose and we can calculate what is z transpose z, right. So, z transpose z in this case would be this, and z transpose y would be 6.2 and 16.29, right. Or we could have employed this one n sigma x sigma xi square, I varying from 1 to n, right, sigma y yi xi. So, either we can use z transpose z into A is equal to z transpose y, or we could have used this. In both cases we will get the same coefficient matrix and right hand side vector, right. So, if we solve that, we will get a naught is equal to 0.46 and a1 is equal to 0.39. Remember, what we are interested is in this c and this uppercase A, right. So, now that we know a naught, right. So, we can calculate what is c using this relation, that we know that a naught is equal to ln c. So, c So, c can be calculated from that expression, a naught is equal to ln c, right. So, c we can calculate, and a1 is nothing but the value of the constant coefficient a in this original model, right. So, a is directly equal to a1 because of this transformation. So, a is equal to 0.39, c is equal to 1.58. So, our model is y is equal to c 1.58 e power a x 0.39 x. So, this is our model, right. So, what was a nonlinear model? We used data linearization to convert into a linear model, right. In this case it happened to be simple linear least square, right. So, we can either use this formula or we can use that analytical solution z transpose z into A is equal to z transpose y and solve for the coefficients of A, right. And then if there is a data transformation, we need to appropriately do the data transformation to get the original model coefficients. So, this is an example for nonlinear least squares using data linearization. So, some of the other examples for linearization, these are 3 other examples wherein we can linearize. So, the actual model is y is equal to alpha 1 e power beta 1 x, right. So, x and y is given, our task is to find out alpha 1 and beta 1. So, if we transform this, so if we take ln on both sides, right, in this expression if we take it will be ln y is equal to ln alpha 1 plus beta 1 x ln e, right. So, this is going to be 1. The regression that we are doing is between ln y, right. So, let us say that is this uppercase y, ln alpha 1 will be the intercept, right, and the slope will be beta 1, right, and there is no transformation in x. So, if we are to solve this model, this nonlinear regression problem, we can actually do a data linearization and actually work with ln alpha and x, right. Over here in the second model, if you see, it is y is equal to alpha 2 x power beta 2. So, here we can take log y is equal to log alpha 2 plus beta 2 log x, right. So, log y, let us say it is uppercase y, log alpha 2 will be our intercept plus beta 2 would be our slope, log x, let us say it is uppercase y. So, we perform a regression between log x log x and log y, or uppercase x and this uppercase y. So, the regression that we are doing is in this space over here. So, over here what we can do is we can take a reciprocal. So, if the model is like this, y is equal to alpha 3 x by beta 3 plus x, we can take a reciprocal of this, right. So, if we take a reciprocal of that, what we will have is 1 by y is equal to beta 3 plus x divided by alpha 3 x, right. So, this will be 1 by y is equal to beta 3 by alpha 3 x plus 1 by alpha 3, right. So, this will be 1 by y, let us say it is uppercase y, 1 by x, let us say beta 3 by alpha 3 is, let us say 1 by x is uppercase x, right, plus 1 by alpha 3. So, this will be our intercept, beta 3 by alpha 3 will be our slope, right. So, here we are working with uppercase x and uppercase y, where uppercase x is 1 by x and uppercase y is 1 by y. So, this is one way wherein we can convert nonlinear regression problem into linear regression problem, right. So, some of the other examples are given over here, right. So, these are taken from Matthews and Finks. So, all these figures have been taken from Chapra and Kunnel, numerical methods by Chapra and Kunnel. So, these are some of the other examples for nonlinear models which can be converted into linear. I would leave it to you for you to figure out how to do it, right. You can look into this book, Numerical Methods Using MATLAB by Matthews and Finks. It has a few more examples, right. So, for example, this particular model, if you see, what you can do is y by L is equal to 1 by 1 plus a e power b x, right. So, we can take a reciprocal of this, L by y is equal to 1 plus a e power b x, L by 1 minus 1 is equal to a e power b x. So, ln of L by y minus 1 is equal to ln a plus b x ln e, right. So, in this case the unknown coefficients are a and b, right. L is known, L is given, right. So, this can be calculated, right. This is, let us say a naught plus a1 x. So, a1 is nothing but b, a naught is nothing but ln, and y is nothing but this expression, right. So, we know how to solve this, both linear and nonlinear regression, right. So, for linear regression, once we apply the stationary conditions, the nonlinear optimization problem got converted into a set, solving a set of simultaneous linear equation. For the nonlinear models that we discussed as part of this session, it turned out it got converted into a set of simultaneous nonlinear equations, right. So, and we also have seen that some of the nonlinear models can also be converted into linear model using data linearization.